So last few videos we talked about double patterning, which was essentially introduced at the 65 nanometer node. We also talked about EUV, which scales this wavelength from 193 nanometer to down to 13.5 nanometer. An important question to ask looking at this picture is that how the heck did we continue to scale and continue to print these pitches down to 65 nanometer from a wavelength of 248 nanometer? And so how did we continue to scale the pitch in this era? And certainly we must have developed some tricks to manipulate light to print at much smaller features in the wavelength, and are we continuing to use those tricks as we go forward? So what I want to describe in this video are these resolution enhancement techniques, which are essentially a set of tricks which allow you to print spacing or achieve a resolution of what is much smaller than the wavelength of light you're using. So all of that is governed by this simple equation, which is called Rayleigh equation, given by Mr. Lord Rayleigh himself. And what it describes is that the minimum feature size that you can print is denoted by this letter D, is proportional to the wavelength of the light you are using. It's inversely proportional to the numerical aperture, and it has a proportionality constant which is called K, and it essentially just relates for a given wavelength and a given numerical aperture what is the minimum distance that you can print. So most of the resolution enhancement techniques, they involve playing with one of these three vectors. So lambda scaling, we already mentioned that it's basically stuck, and if you want to scale it further you need to go to EUV. So what you are left with are essentially these two parameters that you can play with. You can either play with this proportionality constant, or you can play with this numerical aperture. So so these are some of the resolution enhancement techniques that I'll describe to you. So the first of them is immersion lithography, and that essentially deals with increasing this numerical aperture so that you can reduce the minimum dimension you can print. The other of these techniques are related to how do you manipulate the source of the light or the mask that you're using for lithography to essentially allow you to operate at lower K. So they allow you to operate at lower K. So let's look at them one by one. Let's look at immersion lithography first. Shown here is a typical setup that you'll see in any lithography system, where you have a source of a light and it passes through a mask, and when the light is passed through the small feature of the mask, there's a diffraction of light which occurs over here, and there are different peaks associated with diffraction. There's a first order diffraction, there's a second order diffraction peak, and then you have a lens. The purpose of this lens is to capture as many diffraction peaks you can, and then focus them back together to your wafer where you print on your die. So the numerical aperture is given by this very simple equation, where numerical aperture is defined as n times sine theta, where n is your refractive index, and this sine theta or this theta is a reflection of how many of these diffraction patterns are you able to capture. So higher, the more the number of diffraction patterns you capture, that is bigger you make your lens, bigger is your theta, and correspondingly bigger is your sine theta. So one way to increase your numerical aperture is to increase this theta or increase this sine theta, but sine theta being a bound variable, it only stays between 0 and 1. So you can, people did in fact increase this numerical aperture by making a bigger lens, so you can capture higher orders of diffraction, but you can only make this theta go up to 1. A more practical limit is 0.93. So your numerical aperture is essentially then defined by 0.93 times your refractive index. So this is an even simpler equation, and looking at it, the only way you can increase your numerical aperture now is to increase your refractive index, and that's where immersion lithography comes into picture. So what immersion lithography involves, it's a very simple concept. What you do is you insert water between your lens and your wafer. So then the refractive index of this medium, instead of being 1 for air, it becomes now 1.43, which is the refractive index of water. And now your numerical aperture, instead of being 0.93, it can go up to 1.35. So you might have seen when you put things in water, you see them more clearly. It's the same concept over here. You immerse your wafer, immerse basically water between your lens and your wafer. So you'll have a puddle of water here, and you'll have water coming in from here and water going out of here, and that's how it's designed in the current lithography system. And this image over here, it just illustrates again the advantage of immersing into water. And what it shows essentially is that if you immerse in water, your refractive index now changes from 1 to 1.43. And so for a given depth of focus, now you can print a much smaller resolution, or for the same resolution, now you can have a much higher depth of focus. And so this is what immersion lithography helps in doing, and it has been in production for a number of years now.